this video, we will discuss the continuity of a function of multiple variable and how we can determine if the function is continuous at a given point or not. Starting with the concept of continuity, when we are discussing the continuity in a single variable, we means that the function behaves smoothly at a point. Means at that point there is a no jump, no gap and no breakage. For a function of multivariable, continuity means the same thing, but we need to consider more things in a multi-dimension. To say that the function fx comma y is a continuous at a particular point, suppose a comma b, we need these three conditions. First is the function at that point must be defined. This means there is an actual value of a function at a b. Next, we need the limit of the function approaches to that point to exist. This means that as we get closer and closer to this point from any of the direction, the value of function must approaches to the single value. Finally, for a function to be continuous at a particular point a comma b, the value of function at that point must be is equal to the limit of function as x comma y approaches to a comma b, that is same point. In other words, there should not be any sudden jump or a gap in the function value at that point. When these three conditions are met, we say that the function is continuous at a particular point. Now, how we can visible the continuity in a multivariable function? Imagine any surface representing a function in a three dimension. If the function is continuous at that point, means the surface is smooth at that point. But if it has a discontinuity at that point, we might see a break or gap in the surface. For example, the surface could have a hole at that point, or it could be a jump to the different height. In these cases, the function would not be a continuous at that point. Here we have taken the graph of the function x square minus y square divided by x square plus y square. You can observe that this function is not defined at the origin, as there is a hole at the origin. In this case, when the function is approaching to the origin, the function value approaches to the different value depending upon the path. This indicates that limit does not exist at origin. Whereas this function behaves smoothly away from the origin but has a gap or a hole at the origin. In this case, we can say that the function is continuous at everywhere except at origin. Here we have taken the first example. In this example, we need to show that the function is continuous at origin. For that, first we will find the function value at origin. According to this function value at origin is 0. Now to show the continuity, we need to check if the limit of this function exists at origin or not. So for that, evaluate the limit of the function at origin. Function is x raised to power 4 y minus 3 times of x square y cube plus y raised to power 5 divided by x square plus y square whole square. By direct substitution, x is equal to 0, y is equal to 0, we have indeterminate form 0 by 0. It means we need to use some alternative way to find the limit of this function, as this function is not defined directly. Observing the denominator term contain x square plus y square. It is convenient to use the polar coordinate to evaluate this limit. For that, we will replace x with r cos theta and y with r sin theta. Substitute x is equal to r cos theta, y is equal to r sin theta. We have this, and in this case, we take limit r approaches to 0. From here, you can observe that r raised to power 5 is a common term in a numerator. So we can write this as equal to limit r approaches to 0, r raised to power 5 cos raised to power 4 theta into sin theta minus 3 times of cos square theta sine cube theta plus sine theta power 5 divided by, in denominator we have r square, so we can take r square common. Again it has a square, so we have r raised to power 4 into cos square theta plus sine square theta. It's a square. Cos square theta plus sine square theta is 1 and the square of 1 is again 1. Further simplify this is equal to r. So we have in this case limit r approaches to 0, r times of, suppose this term is equal to a, divided by 1 square. So here a value is equal to this term. Now when r is approaching to 0, this function is approaching to 0. It means the limit in this case is equal to 0. Since the limit as x comma y approaches to origin is equal to the function value, so we can conclude that the function is continuous at the point 0, 0. Next example is check whether the following function is continuous at the origin or not. First step, we will take the function value at the origin. According to this function, the function value at origin is half. Secondly, we need to find the limit of the function as function approaches to origin. Now, in order to find this limit, we need two results. In one variable, when we are taking the limit of sine inverse x by x as x approaches to 0, this is always 1. And the same result we have for the tan, that is the tan inverse x by x. This is also is equal to 1. Same result we can apply in this case, but for that we need to convert this two variable into one variable. So let x plus 2y is equal to t. Now as x, y is approaching to 0, 0, it means t is also approaching to 0. So we can rewrite this as limit t approaches to 0, sine inverse t divided by tan inverse, and in this case it is a 2 times of t. Now we need to apply this result. For that we need a t variable in this case. So what we can do, we can write this as equal to limit as t approaches to 0, sine inverse t by t as well as multiply by t. As per this result, the limit of this function as t approaches to 0 is equal to 1. But in this case, it is not is equal to 1 because in tan inverse, we have 2 times of t and here we have a simply t. So we need to create a 2 times of t. For that, multiply by 2 and divide by 2. Now in this case, this function is approaching to 1 whenever the t is approaching to 0. So this is equal to 1 times of 1 by 2 into 1. And hence this function is approaching to half as it is approaching to origin. Now what is the function value? Function value is also half. So we can say that the limit of this function at origin is equal to the function value. Hence the function is continuous. Next example, check whether this function is continuous at origin or not. Steps are same. Find the function value at origin. Function value at origin is 0. Second is we need to find the limit of this function as function approaches to 0. It means we need to find the limit of this function at origin. For that, if we substitute direct value of x as a 0 and y is equal to 0, we are getting an indeterminate form 0 by 0. It means we need to choose some another way. One way we can observe from the denominator, it is has a x square plus y square. It means we can convert this Cartesian function into the polar function, and after that we can find its limit. For that we will let x is equal to r cos theta and y is equal to r sin theta. And this limit is r approaches to 0, r cos theta minus r sin theta, its square, divided by x square, that is a r square cos square theta, plus y square is r square sin square theta. This is equal to limit r approaches to 0. From numerator we can take r outside, but it has a square, so we can take r square outside. Remaining term is cos theta minus sin theta whole square divided by r square common from this factor, and the remaining term is a cos square theta plus sin square theta. R square is get cancelled with r square. We have limit r approaches to 0 cos theta minus sin theta square divided by 1, because cos square theta plus sin square theta is 1. In this case there is a no r, or we can say the limit in this case is a cos theta minus sin theta. As the limit depends upon theta, it means it is a path dependent. So if it is a path dependent, it means limit does not exist. So in this case, this limit does not exist. If the function limit at origin does not exist, it means the function cannot be a continuous. In this case, function is not continuous at origin.